Hello everyone, welcome to our first lecture in the series of lectures on discrete mathematics. We are going to cover textbook Discrete Mathematics Elementary and Beyond by Lazlo Lovasz. In the first lecture, we are going to discuss about very basics of counting. In different scenarios, how do we count? So the story goes like this. Alice is our main character. She is going to throw a party to her friends. Let's suppose it's end of semester and she is going to call her friends over a party at her home. So she invites Bob, Carl, Diane, Eve, Fred, and George. So it's just like Alice is A, and then we have B, C, D, E, F, G. Alice, Bob, Carl, Diane, Eve, Fred, and George. So all her friends come to her room, come to her home, and they greet each other. So each and everyone is going to shake hand with each and every other person. So suddenly a question arises, how many handshakes did we have? So we are seven people and each and every person is going to shake hand with each and every other person. So if we are going to count our handshakes, so obviously no one is going to shake hand with himself or herself. They are going to shake hand with rest of the six people. So someone said it should be 42 because we are seven people, each and every one is going to shake hand with the rest of the six people, so it's going to be 7 times 6. But suddenly Alice is a wise girl, so she thought maybe we are doing some overcounting. It's not actually 42 because when one person is going to shake hand with other person, so we are going to count this handshake twice because A is shaking hand with B and B is shaking hand with A. A is counting this handshake to his count and B is counting this handshake to his or her count. But actually it is one handshake, so we are going to count one handshake twice. So we should divide our this count by a number 2. So actually it's 42 divided by 2, so we are going to have 21 handshakes. Everybody agrees, yes, it's true, it's going to be 21 handshakes. And actually we can count it in a different way, like if we have 7 people, the first guy is going to shake hand with 6 of the people, and then the next guy he is going to shake hand with 5 of the people, because one handshake we have already counted, so he will have 5 new handshakes. So we have 6 plus 5 handshakes, and the next guy is going to shake hand with 4 new persons. There will be 4 new handshakes, so 6 plus 5 plus 4. And then next person is going to shake hand with 3 people, next is going to handshake with 2 people, and at the end there is one pair, they will handshake with each other, so that there will be one handshake. So this is going to be 6 plus 5 plus 4 plus 3 plus 2 plus 1, which is eventually 21. So we can count one thing in two different ways. So we can count like counting each and every handshake. We can list down those handshakes. So it's going to be 6 plus 5 plus 4 plus 3 plus 2 plus 1, 21. Or we can have like 6 times 7, 7 times 6 divided by 2 is 42 divided by 2, 21. So we can have a general formula for this thing. If we have n people, each and everyone is going to shake hand with n minus 1 people. So it's going to be n times n minus 1. But each handshake is going to be counted twice. So we need to divide it by 2. So this is going to be n times n minus 1 divided by 2. So we get a general formula for handshake. So now it doesn't matter how many people we have. We have 10 people, or we have 100 people, or we have 1,000 or 1 million people. So we can easily count handshakes. N into n minus 1 divided by 2. And actually this is a famous theorem. We call it handshaking lemma. When we have some entities, let's suppose n entities, and they are going to have certain relationship among each other. Each and every element, each and every entity is having some certain relationship with each and every other person. So then we call it a handshaking lemma. And how many relationships we have? We have n into n minus 1 divided by 2. For example, in this example that we just did it, so the relationship was handshaking. So how many handshaking we had? It was n into n minus 1 divided by 2. So computer science scientists often, when they're going to design algorithm or solving some problem, so They use a very interesting tool, it's called graphs. So different entities, nodes, they are going to have some links between them, a relationship between them. We call it edges. So if we are going to draw a graph of these 7 people who are going to handshake with each and every one, so this is going to be something like this. So these blue dots are representing our 7 individuals: Alice, Bob, Carl, Jan, Eve, Fred, George. And each and everyone is going to handshake with each and every other person. So handshake is represented with these lines, these edges. So suppose this is Alice, so she's going to handshake with all of her 6 friends. Bob is going to handshake with each and every other person. And if we carefully count these edges, these are going to be 21 edges. N into n minus 1 divided by 2. Usually such kind of graph is called complete graph. We represent it by k. So if there are n nodes, vertices, dots, so this is called k with subscript n, kn. So there are n nodes, and how many edges will be there? N into n minus 1 divided by 2. If you just if you don't have background in the graph, so you can have a brief look on Wikipedia to see graph, and especially complete graph. So you can see if we have 2 nodes, they will have 1 edge, and uh, it is valid with this formula, n into n minus 1 divided by 2, because there are 2 edges. So 2 into 2 minus 1 divided by 2, we will have 1 edge. And then we can see k3, a complete graph on 3 nodes, 4 nodes, 5, 6 and 7 nodes, and so on. We can have any number of nodes, we can draw a complete graph on it. So complete graph is called kn, a node on n, a graph on n nodes. And if we are going to count number of edges, number of links, so it's n into n minus 1 divided by 2. So let's go back to our party. So they have shook hand with each other, and now they are settled down. They sit down around a table. So suppose we have a round table across which our friends are sitting down. So we make something like this, that Alice is going to sit at the head of the chair, and all rest of 6 guys, they are sitting around the table. Suppose B is sitting over here at the first place, then C, D, E, F, G. They are having chit chat with each other, and then suddenly they decided, we should switch seating with each other, because it's not fun to have just one seating arrangement, so we cannot talk to some other of our friends. They decided, okay, let's make plan like this, that we are going to change our seating arrangement after every half hour, and we are going to try each and every possible seating arrangement. If B is sitting next to C, then at some time B and C should switch seats with each other, and then maybe C and D should switch seat with each other, then maybe B and F should switch seat with each other. We keep it like A is sitting at its place, Alice is sitting at her place. Alice is not going to change her seat. So if we fix seat of Alice, how many seating arrangements we are going to have? So for the first place, suppose this is the first place, so we are going to have 6 choices. We can place Bob, let's call it A, B, C, D, E, F, G. So we can place B or C or D or E or F or G at the first place. So for the first seat, we have 6 choices. We exclude Alice because her seat is fixed. So we place any one of those 6 people at the first seat, and then for the next seat, how many people we have? Now we have five people, because for the first seat we have placed any one of these 6 guys. So one person is fixed, 5 persons are left. So for the second seat we have 5 choices. Any one of 5 person can sit on the second seat. And then for the third seat we have 4 choices. For the for the fourth seat we have 3 choices. And then 2 persons are left. For the fifth seat we have 2 choices, and at the last seat we have 1 choice. So for the first seat we can choose any of the 6 persons. 1 person is fixed. For the second seat we can choose any of the 5 people. So far how many seating arrangements we have? For the first 2 places, 6 times 5, because for each of the choice at the first seat we have 5 choices for the second seat. So it's 6 times 5, 30 choices. And then for the next seat we have 4 choices, so it's 30 times 4, we have 120 choices. And then for the next we have 3 choices, then 2 choices, and then 1 choices. So this is going to be 6 times 5 times 4 times 3 times 2 times 1, which is 6 factorial. 6 factorial is 720. So they are going to have 720 possible seating arrangements. And if they are going to change their seating arrangements after every half hour, so that means we need 720 half hours. So that means 720 times half, which is 360. So this part is going to be for 360 hours. And yeah, we can count it in days. It's going to be 15 days. 360 divided by 24 hours, so it's going to be 15 days. So this is quite a long party, so we are going to have a long time with this. And just imagine if we are going to change the seat of Alice, so all this thing is going to be multiplied by 7, because then seating arrangements will be 7 factorial. Everything will get multiplied by 7. So that means 7 times 15 days, 105 days this party is going to happen. So that's better if we keep Alice at her fixed place and only 6 people are changing their seats. Still we are going to have a long party for 15 days. So how we proceed? So they sit down, they are having chit chat with each other, and then they started getting bored. Of course, it's quite long party. So someone suggests, suppose Bob. Bob suggested, we are 7 people over here. Let's buy lottery tickets, and we are going to buy enough lottery tickets that we for sure are going to win the jackpot. No matter what will be the lottery ticket, winning lottery numbers, we will have that combination of lottery numbers with us. So we should buy enough tickets, a huge amount of tickets. So the rules of the party is like, when you get lottery ticket, so there are 90 numbers on it, and you have to cross 5 numbers out of these 90 numbers. So for the first number, when you are going to cross it, so you can cross any of the 90 numbers. It's your choice. And for the next number you are going to cross, one number you have already crossed, so it's going to be 89 numbers which you are going to cross. And one of 89 numbers, you have 89 choices. So when you cross second numbers, 2 numbers are excluded. Now you have 88 numbers. That for the third number cross, you have 88 choices, so you will cross one of those 88 numbers. 3 numbers are crossed, 87 numbers are left. So for the fourth number you have 87 choices, and for the fifth number you have 86 choices. So how many possible tickets they may have, and obviously the winning combination will be one of those. So when they are going to count, they see that actually it's going to be a very huge number. So they need to buy something 90 times 89 times 88 times 87 times 86 tickets. So this is quite a huge number. I mean, you can just see it is going to be 90 raised to power 5, something less than that. It's the number is like 86 raised. If we are looking at the biggest number, it's 90. Smallest is 86. So it's somewhere 90 raised to power 5 less than that, and 86 raised to power 5 more than that. It's going to be quite a huge number. And then suddenly Alice is a wise girl, so she thought, maybe we are doing overcounting. Just like in handshaking we did overcounting, so again we are doing overcounting. Because for example, if we are going to have this winning number 3, 6, 27, 32, 42, so does it matter that these 5 numbers 3, 6, 27, 32, 42, these are 5 numbers, doesn't matter in which order they appear. If I have these 5 numbers with me crossed on my lottery ticket, doesn't matter 6 appears first or 3 appears first, 27 appears first, or any of these number appear first, any of these number appear second or third, fourth, fifth, because on my lottery ticket I have crossed these 5 numbers in whatever order I have crossed. Because when we count 90 times 89 times 88 times 87 times 86, we took care of the order, which number I'm going to cross first and which number I'm going to cross next and which number I'm going to cross next. But when these five numbers appear after the lucky draw, so it doesn't matter in which order I have crossed, because on my lottery ticket these are just five numbers crossed. So if it is 3, 6, 27, 32, 42, or this is 6 appear first, 6, 3, 27, 32, 42, or any other order, I have these five numbers, so I can claim my jackpot. So then question arises, for example, if we have these five numbers, in how many ways we can order these five numbers? So this is exactly like seating problems, a seating problem that we just solved. In seating arrangement, if we have six persons, six seats, so there are going to be six factorial seating arrangements. So now we have over here five numbers in five places. So in how many ways I can order these five numbers? It's 5 factorial. For the first place, any of these five numbers may appear. For the second place, any of the rest of the four numbers may appear. For the third place, any of the rest of the three numbers may appear. For the fourth place, we may put any of the two numbers, and the last place, we will have the last one number. So 5 times 4 times 3 times 2 times 1. So 5 factorial numbers, 120. 5 factorial numbers are those which we are counting again and again in this multiplication. So those 5 factorial combinations of these numbers are eventually the same ticket. So we should divide this number by 5 factorial. So this is going to be, so for 90 times 89 times 88 times 87 times 86 divided by 5 factorial. 5 times 2, 4 times 3 times 2 times 1. But still it's a very huge number. It's like 43,949,268. So they need to buy that many tickets to have all possible combinations of lucky draw numbers. So then they can win no matter which number comes. They always have that combination. This is huge number. Alice says, even if we sell our home where we are sitting, still we cannot buy these many numbers, so it's not a good idea. Let's think about some other thing. So they are going to have a long party for 15 days. They decided, let's do something. So they decided to play cards. Bridge, and bridge rules are, we have 52 cards in our deck of cards, standard card. So we have four suits of 13 cards each. In each suit we have four suits. So bridge rules are like, we are going to distribute cards among four players, and every player is going to have 13 cards. So we randomly give 13 cards to each player. And suddenly George is going to make a strange claim. He says, I've got exactly the same cards as before. Like in the previous game, that cards, 13 cards I got. In this game, I have got exactly those 13 cards in my hand. So everyone is surprised and they have some doubts on his claim. Oh really? Have you got the same number of cards? The same cards, exactly the same cards. George is very confident, so everyone decided, okay, let's count the chances of getting the same card on next turn. So what are the chances this thing to happen? So they calculate all possibilities of a hand of 13 cards a person may get, and then they see how many possibilities are there. So what will be the chance of getting the same hand next time? So if you are going to count, so it's going to be exactly like lottery problem. Like we have 52 cards. For the first card, a person is going to have 1 out of 52 cards. So there are 52 possibilities that a person will get some card of one of those 52. So he has got first card, and then for the second, we have 51 choices because first card already is in my hand. So for the next card, we have 51 choices. For the third card, we have 50 choices. For the fourth card, I will get one card out of rest of the 49 cards, 49 choices, and then 48 choices, and so on and so on and so on till I reach to 40. For the last 13th card, I have 40 choices. So I will get 13 cards. So how many possible ways are there to get 13 cards? It's 52 times, 51 times, 50 times, 49 times going down till 40. So from 52 coming down to 40, we multiply these numbers. This is going to be a huge number, obviously. It's something like, I mean, if we approximate, it's going to be something like 50 or 45 raised to power 13, which is a quite huge number. And suddenly Alice, Alice is a wise girl, so she again said that, oh, we are doing overcounting, because it doesn't matter in which order a person gets 13 cards. If he get one card at the first time, or he get the same card in some other way of distributing the cards in the middle or at the end. At the end, he is going to arrange those cards at his own choice. So it doesn't matter which card comes first or which card comes second or third or fourth or the last. So again, it's just like lottery problem, in which it doesn't matter in which order we cross the five numbers. So in this case, again, it doesn't matter in which order those 13 cards come. So there are 13, suppose we have got 13 cards. In how many ways I can arrange those 13 cards? It's 13 factorial. 13 times 12 times 11 times going down till 1. 13 factorial. So it means there are 13 possible ways of getting 13 factorial ways of getting 13 cards. So I'm going to count these numbers again and again, which are actually the same. So I need to divide my actual number of ways of getting cards by 13 factorial. So we divide 52 times 51 times 40 divided by 13 factorial. And what number is it? This is going to be 635 billion 13,559,600. So this is a huge number. So possible hands that a player can get out of 13 cards, with 13 cards out of 52 cards, is like more than 600 billion. So it's just like when we are playing some game with the dice. So what is the possibility, what are the chances of getting certain face on the dice? Dice has 6 faces, 1 2 3 4 5 6. So every face has 1 out of 6, 1 by 6 chance, which we call probability. 1 by 6 probability to get one face. And if we are going to roll the dice again and again and we take average of certain face, so we can see that each and every face may come almost 1 over 6 times. So just imagine we have a big dice of almost 600 billion faces. So if we roll it, we get certain face, certain outcome. And what are the chances that the same face will appear again? It's 1 out of 600 billion chances. So which is highly unlikely this thing to happen. It means if we are going to play around 600 billion times on average, the same combinations, exactly the same cards will come in my hand again. So all of the friends said to judge, no, we don't believe this claim of yours. It's highly unlikely that you will get the same cards as before. Okay, so they played chess, and then they played chess for a long time, because they are going to have a huge party. And then they, on the maybe on day number 10, they decided, okay, it's enough with the cards, let's do something else. So they decided to play chess. So Alice decided, okay, you people can play chess. I'm going to make pizza for you people in the kitchen. I will be busy, so you people can play chess. So they set up 3 chess boards. Let's name these 3 chess boards X, Y, and Z. So they have 3 chess boards, and against each chess board, 2 players are going to play against each other. And then they suddenly they thought, okay, each and every person should play match against each and every other person. So how many possible matches we are going to have? So when they are going to count number of possible matches, so they thought we are going to have 6 players sitting around the chair that's sitting around the table. So if we are going to switch our chairs one by one, so we will going to have different matches. So it means we are going to have something like problem. So we are going to have like if we keep on changing our seats, so we are going to have 6 factorial, just like seating arrangement problem, 6 factorial possible matches. Suppose we have one combination of matches. Bob is playing against Carl, Dion is playing against Eve, Frank is going to play against George. So they in the next game set of games, they are going to change the seating arrangement, so they will have different opponents. So they decided, okay, we are going to have 720 matches. But someone said, maybe we are doing overcounting. We are going overcounting because it doesn't matter. Bob is sitting on the right side of the chessboard or he is sitting on the left side of the chessboard. Carl is sitting on the left side of the chessboard or sitting on the right side of the chessboard. Eventually, it's a match between Bob and Carl. So we are counting this thing as twice. So we should not count it two times. It is just like only one match, so we should divide 720 divided by 2. But then the same thing happened with Diane and Eve. It doesn't matter Diane is sitting here or Eve is sitting here on the other side. And same thing happens with Frank and George. It doesn't matter on which side Frank or George is sitting. Eventually it's match between Frank and George. So it means we have to divide by 2 and divide by 2 and divide by 2. We have to divide by 2 3 times. That means 2 times 2 times 2, which is 8. So we should divide 720 divided by 8. So we should have 90 matches. But then someone said, still we are overcounting. Does it matter? Bob and Call, they are playing match on chessboard X or chessboard Y or chessboard Z. Eventually, it's a match between Bob and Call. And same thing happened with any other pair, Dion, Eve, Frank, George, or any other combination of these players. So it doesn't matter on which board they are going to sit. So how many overcounting we are doing? So for example, we have X chessboard. We take this one. So for X, what choices we have? If we are going to these set of players, so we can make Bob and Carl sit on X, or we can make Diane and Eve sit on X, or we can make Frank and George sit on chessboard X. So we have 3 choices to make a team sit on board number X. And when we make one team sit on X, we have 2 choices for chessboard Y, and then we have 1 choice for chessboard Z. So this is going to be 3 times 2 times 1. So 3 times 2 times 1, 3 factorial, which is 6. So 6 times we are overcounting when we counted 90 matches. Actually, it's not 90 matches. When each and every player is playing against the other one, it should be 90 divided by 2. So this is going to be actually 90 divided by 6 is going to be 15 matches. So eventually we are going to have 15 matches. So they come to this conclusion, and then Alice comes and asks what you people are doing. They said we are counting how many matches we are going to play against each other. We counted like this: 720 divided by 8 divided by 6, so it's 90. Alice suggested we have another way of counting this. Why you are counting in such a complicated way? We can fix one player. Suppose we can take alphabetically order. So we choose, suppose Bob comes first. So Bob, we fix Bob for any one of the chessboard, that doesn't matter. And then Bob has to choose one of his opponent. He can choose any one of the rest of the 5 players. So he has 5 choices to choose. So when Bob has chosen one person, 1 out of 5, so he has 5 choices. One person he has chosen, so this pair will sit on certain chessboard. So now we have 4 players. So we can take one of these 4 players, and then he or she has to pick one of his opponent. So she or he will have 3 choices because now 3 players are left. So total choices are now 5 for the first pair and 3 for the second pair. So 5 times 3. So these two players sit down on some chessboard. Now we are left with only 2 players. So they obviously they don't have any choice. They have only one choice. They have to play against each other. So our answer should be 5 times 3 times 1. So even again it's 15. So we counted same thing in different way. First we counted the way like 720 divided by 8 divided by 6, we get answer 15. And now we are counting the same thing but in a different way. We fix one player, and this one player is going to choose its opponents, one of 5. So he or she has 5 choices. They get separate. For the rest of the 4, again we fix one person. He or she is going to choose one of 3 players. So he or she has 3 choices. So total choices are 5 times 3. And then we have 2 players. So obviously they just choose each other. So there's only one choice. So it's 5 times 3 times 1. So we have 15 choices. So answer should be obviously same. So it's 15. And then suddenly says, oops, actually it's just a handshaking problem because each and everyone has to play a match against each other. So this is just like we are going to handshake with each other. So it's just like handshaking problem. So it's n into n minus 1 divided by 2. 6 players, so 6 times 5, 30 divided by 2. We are going to have 15 matches. There are 15 possibilities of having match. Each person is playing match against other one. So they had uh, good matches of chess playing against each other, and then after that they may have their pizza, and over here the party ends at happy note and we leave the party. Thank you very much. Merci beaucoup. Au revoir.